Hello everyone and welcome to part 2C of homework 2 of computational methods, and today we're going to be implementing Broyden's method with step size adjustment and inversion of the Jacobian as necessary. So let's start with defining what Broyden's method is. So Broyden's method is an extension of Newton's method for finding roots for nonlinear systems. For example, systems that have more than one equation and more than one variable. So Newton's method, which we talked about in the last video, was basically a method for solving it that uses the Jacobian for each iteration. And the idea behind Broyden's method as a step to it is, instead of actually calculating the Jacobian at each iteration and then transposing it, Broyden instead approximates the Jacobian using algebra rather than actually finding the partial derivative matrix. So doing it this way is faster, and it's a lot faster computation, especially when you're trying to transpose massive matrices. Doing it with this approximation should be a lot easier. Okay, so here are the equations for solving a system of nonlinear equations. And ultimately it uses this very similar equation to the Newton's method, where we have x, each step size of the new x value, or in this case, the new x vector, is just equal to the previous one minus the function solved for the x vector times the inverse Jacobian of that at that same point. However, we're going to use the Sherman-Morrison formula shown here as a kind of way to approximate this Jacobian without actually solving for it. Okay, so let's get to it. So first thing we're going to do is we're actually going to straight copy and paste our Newton's method, since it's so similar. Let's call this Broyden's. Okay, so now that we have this is just our, so this is our same function from the Newton's method. I'm going to put some spaces here so we can add more as we go. So as you can see here, we give it a function, an initial guess, x naught, max iterations, and tolerance. First thing it does is it calculates the Jacobian at x at that initial guess, which is found right here. Then it solves for f naught. So what we're going to need to do is, let me split screen this so we can see these formulas as we go. Okay, so the first thing what we're going to do is we're actually going to want to make this Sherman-Morrison formula here. So let's put that at the top of the screen here, this guy here, and we're going to code that here. And let's call it J inverse is equal to the previous J inverse plus this function here. So let's code this out and then we'll define all these terms. So this one is just a delta x minus our our inverse Jacobian times, keeping in mind that this Jacobian and then the function that follows it are both matrices, so we have to use the matrix multiplication rather than our normal multiplication operation in Python. So that's delta f, which we will define in a second. So we have this, then we're going to multiply this by the second term here. So multiplying that by delta x, the transpose of delta x specifically, which is multiplied by that same inverse Jacobian. Let's make sure we got everything. Okay, that looks like everything on the top. Now we're going to divide it by this denominator here, which is another delta x transposed times our inverse Jacobian again, times this function, here. So that's our delta f. Okay. So now that I coded out the Sherman-Morrison formula, let's define all these terms that we just used. So our delta x is equal, as defined up here, is our x sub n minus the previous one. Actually, we might want to do this. Let's define this within the for loop, so that it'll change with that equals x1 Our delta f is going to be the same way. It's f1 minus f naught. So then we have this. And just like with the Newton's method, we're going to look for the norm of f1. Once the norm of our functions drops below our tolerance, that's when we're going to break it. And that's when we're going to get our final answer. Okay. So running this, do we have everything we need? So we have delta f, we have delta x, we have our inverse. Oh, we need to define our first inverse Jacobian, which is, so we're going to, as an initial inverse, we're actually going to take the inverse of this Jacobian that we just calculated. Which is okay. So you'll notice with this equation here that we have our xn plus 1 equals xn minus this. Well, xn plus 1 and xn, if you subtract one from the other, you get delta x, right? So actually, what our delta x ends up equaling is it equals this right here, this inverse Jacobian times the function solved at x0. So we can actually rewrite our delta x as equal to that negative inverse Jacobian times f0. And our delta f stays the same. So let's run this, see if there are any errors, syntax errors right off the bat. Okay, seemed happy with that. Actually, we need to run this first, don't we? Because that has our... So we run that, good, no issues. What's next? I think we got everything we need. So let's code up a function to test this. So let's just call it fun. And we'll give it an x. Let's use this function that we used in class, or that we've used previously to test this, and just let me copy and paste it. And it's just this. This is a essentially this is an equation that it's two equations with two variables, x0 and x1, and it just gives us a quick two-dimensional or a system of equations for us to test with. So we're going to run that. Then we are going to Broyden. Then let's actually give it an x0. So x0 equals, just make it 0, 0. Make it easy for ourselves. That's x0. And that should be everything we need. Let's run that. Expected a callable value, got x0. Let me define this. Okay, so it wants me to okay, so it's giving me this callable value error because it wants a function and it's getting this. So how do we fix that? First thing we do is we have to figure out why it's not giving us the values that we want. So let's get rid of this and let's just make it use the f to get this Jacobian. Okay, so now that we have a new error, it wants a two-dimensional error and we are giving it a 0. Which part is the 0? Okay, so it's trying to take the inverse. So we're running this Jacobian of this function. See if the error is before or after that. Okay, so it's getting to this line here and being unhappy because of it's taking the inverse of this Jacobian as seen by this. So what that probably means is that we should probably give this Jacobian that we solved for here a value. So we'll run this at x0. Then we should be able to run this. Okay, so it did run, but it went to infinity, which is not helpful. Okay, so what does that mean? So in this case, what that means is that it must have overshot the 0 and just kept going until it just hit that max iteration and was done. So the way a way we can prevent that from happening is by implementing what the problem wants is a step size adjustment. So how do we implement a step size adjustment? So the step size is going to be this delta x right here. That's what it's stepping each time it goes. That's how much it changes is by this negative inverse Jacobian times f0. Well, if we want to make that smaller, how do we do that? And the way we're going to do that is we're going to use a while loop, actually. So let's use a while. And what we want to do is, since the number we're looking for is that linear algebra norm of f1, we want that number to keep getting smaller and smaller and smaller. Well, if it gets bigger, that means that we must have overshot it somewhere. So f1, if it's ever greater than the previous value, so at this point we've defined f1 and we have defined f0 and we have not yet changed it. So while we have that, then let's use some sort of constant that can, some sort of scaling constant that can change as we do the while loop. So let's call that an alpha. And let's just set that equal to 1. And then within the while loop itself, let's change that alpha value to be 0.75 times its previous value. So as it runs and runs and runs, it'll get smaller and smaller and smaller until it's eventually, well, until it's eventually 0. So, gee, let's do it this way. So we're going to need this delta x in there, right? But what we want with this is we have let's update it like this so that we don't have to do this matrix multiplication more than we have to. And so within this loop, we're going to take, define the same inverse Jacobian times f0. And then we're going to apply this alpha value scalar and say, our x1 is going to equal x0 plus our alpha, which as a reminder is shrinking over the more times we do this while loop. And we're going to multiply that by our delta x. Okay? And then we'll calculate f1 equal to f of at x of 1. Okay? So now let's test that. Oops, that should be an f0. Yeah, let's try again. It's a rather long run time. That might be because we have max iteration set at 100. So once we hit, let's say once we hit 30 seconds, okay, well, it finished. And we certainly got a number here. So let's do this just because I'm curious. I'm curious to see what these values are as we go. Oops. Yeah, no, we want that. As you can see, it's ticking and ticking. And this number is getting smaller over time, which is something that we're really happy about. And what it'll do is it'll keep going until it drops below that tolerance we gave it, which was less than 1 times e to the negative 10, which it does not appear that it actually did that. So I wonder if it hit the iteration limit instead. Hide that. Let's print alpha. I should have been more specific there. Looks like alpha frequently falls very, very small. So just based on a quick read, it appears that our alpha value falls very, very small. So let's set a, let's see, so our homework, the description for this part allows us to do inversion of Jacobians when necessary, when progress gets slow. So we're actually going to do that because I think we might have to. And what we want to do is we want to do if our alpha falls below, say 1e to the negative 7, then let's calculate that. Equals let's do it of x. Let's do x1. Then we're going to want to recalculate delta x as actually that's Let's move these afterwards. Be the right indentation. Let's see where that leads us. What do you call Oops, that should be an inverse. Oops. And let's see if we can get away with just doing that. Okay, so we got the same error as before, so same fix as before. Okay. Now we'll see if this ends up any faster than the last thing we tried. I don't think so. So that looks like it hit the iteration limit because these two numbers, our F1 and our F0 and F1, our Fs should be smaller. We would expect them in around the neighborhood of 10 to the negative 8 or so. So let's see, how can we make this a little easier to do? First of all, let's comment that away. I'll comment that away too. Something we can do is to just print the word done when we hit our tolerance limit, just so that we know it's done. Let me check this J inverse function based off of the Sherman-Morrison, just to make sure we got it right. So our new inverse equals the old one plus delta x, which we calculate up here, minus our old Jacobian inverse times delta f, which is f1 minus f0. That's right. Yeah, f1 minus f0. We multiply by this, which is the transpose of delta x times our inverse Jacobian. This times, just throw in extra parentheses here. All this divided by this delta x transposed times our inverse times our delta f. This looks correct. We have this updating. I'll just put the word alpha, so that we know if this ever comes into play. We'll have those. That'll help us debug this. Okay, so it looks like it's hitting a bunch of times. So that means it looks like every time this hits, it has to go all the way to this new number. Interesting. Okay. So it looks like it did not finish. And I hesitate to increase our max iteration because it's already taking 20 seconds to do 100 iterations. What if we comment out this? Let's see if that speeds anything up. Because realistically, our F0 and our inverse are not changing until we hit this here. So let's run that, run Broyden. While it's executing, let's go through this again. Let's see what we need. Okay. Let's expand this one out so we can see what we're doing a little bit better. So first and foremost, if this while loop works anything like our for loop, we might want to put this all in the big parentheses. There. And then what we will probably want to do is let's actually move this behind. And since we're using delta x and delta f to calculate this guy here, let's update them before we get there. So let's do delta x equals just x1 minus x0. And delta f equals f1 minus f0. Let's run that. Let's actually change, let's leave that at 100. Let's run this. Okay, so it looks like it's still running. So last time we ran this, it took 20 seconds to hit its max iteration. And it looks like it still took 20 seconds and did not make it. So that means there's still something going on. Let's just drop this to 25. Okay, so we dropped it to 25, finished very quickly, and still did not reach where it needed to be, which tells us that maybe our steps are too small. So if our steps are too small, then how do we fix that? If our step size is this inverse here, so we have F0, that calculated, we have our inverse Jacobian, which is our inverse Jacobian of our initial guess. Okay, so it's really looking like these step sizes get really small as it falls to 0, which might be the error. It's not falling slow enough. And sure, I could put this at 500 so it would converge, but that takes a while. So how can we increase step size while also be wary of overshooting like we did in the first example? Okay, so so looking into it, oh, that's spelled wrong. Oh, well, look at that. So it was a simple typo. This done here indicates that we hit this, and it broke. So we finished. This was our final norm of F1, and these are our values. So after all that, we were able to implement the method with step size adjustment, and we had to include inversion of the Jacobian only when necessary, which is only here. So the benefit of doing it this way over the previous Newton method is that we only had to do it a handful of times, whereas with the Newton method, we had to do it every time. And sure, with this one where it was only a two-dimensional, or we only had two variables and two equations, taking the inverse of that Jacobian was pretty quick. But once you get, 10, 20, 30, heck, over 100 equations with 100 variables, taking that Jacobian and then the inverse of that can take a lot of time and computing power. And this, using this Sherman-Morrison formula to approximate it, that really helped us. So now the big question that we have left now is why does this work? How did we get there? And that's actually something we'll talk about in the final video where we derive the method. And we can basically derive how it was used to approximate the Jacobian. So join me in part 2D for that. So thank you.